Lesson 3.1 Data Formats for Fine-Tuning. Overview var xia volde. Here's something that trips up almost everyone on their first fine-tuning attempt. The model doesn't care how smart your training examples are if they're structured in the wrong format. Data formatting is the silent gatekeeper of fine-tuning. Get it wrong and nothing works. Get it right and the rest of the process flows naturally. This lesson is about building that foundation correctly from the start. 30 minutes, beginner level. And by the end, you'll know exactly how to structure your data for any fine-tuning project you encounter. Learning objectives. By the end of this lesson, you'll understand the 4 main data formats used in fine-tuning and, critically, when each one is the right tool for the job. You'll recognize the common file formats, JSON, JSON-L, CSV, and Parquet, and understand the trade-offs between them. You'll also understand the fundamental difference between how base models and instruct models expect their training data to look. That last point alone will save you hours of debugging. The 4 main data formats. Balde, Hurmas. The first format is the instruction format, and it's the workhorse of modern fine-tuning. If you want to teach a model to follow directives, this is your starting point. Here's what an instruction format example looks like in practice. You have 2 required keys, instruction and output. The instruction tells the model what task to perform, in this case, writing a professional apology email for a delayed shipment. The output contains exactly what you want the model to produce, a complete, structured email with a subject line, an order number reference, and even a goodwill discount offer. This pairing is the entire learning signal. The model sees the instruction, sees the desired output, and during training it adjusts its weights to make that kind of output more likely when it sees that kind of instruction. The richer and more realistic your output, the more useful the training example becomes. The instruction format has 2 variants. The minimal version uses just instruction and output. The extended version adds an optional input field for additional context. Think of it as the raw material the model needs to work with. Use the minimal version when the task is self-contained. Add the input field when the model needs to operate on something specific, a piece of text, a code snippet, a document. Here's what that looks like. Notice the 3-field structure here. Instruction defines the task. Translate to Spanish. Input provides the specific content to work on. Hello, how are you today? And output gives the ground truth the model should learn to produce. Hola, ¿cómo estás hoy? This separation matters because it teaches the model to treat the instruction as a command and the input as data to operate on, rather than conflating them. Use this 3-field variant anytime your task involves transforming, analyzing, or responding to a specific piece of content. The second format is the conversational format. The right choice anytime you're building something that needs to handle back and forth dialogue. The conversational format is built around a messages array where each element represents one turn in the dialogue. Every message has 2 fields, role and content. The role tells the model who is speaking, and there are 3 possible roles. System sets the overall behavior and persona before the conversation begins. User represents what the human says. Variable represents what the model should say in response. In this example, the system message establishes that the assistant is a customer service agent for tech store, professional, empathetic, solution-focused. The user messages simulate realistic customer problems, and the assistant turns demonstrate exactly how the model should respond. During training, the model learns to maintain that persona and context across multiple turns, which is something the instruction format simply can't teach. The conversational format is the industry standard for chat models: Llama Chat, Mistral Instruct. GPT-style models all expect this structure. The system prompt is particularly powerful. It's where you define personality, constraints, and domain expertise before a single user message arrives. If you're building a customer service bot, a tutoring assistant, or anything that needs to maintain context and tone across a multi-turn exchange, this is your format. The third format is the completion format, designed for tasks where you want the model to continue or complete a piece of text rather than follow an instruction. The completion format is the simplest of the four. A single text key contains raw content, no instruction wrapper, no row labels, just the text itself. In this example, it's the opening of a story about a dragon named Ember. The model's job during training isn't to answer a question. It's to learn the patterns, style, and flow of the text so it can continue writing in that same voice. This format is also used for domain adaptation. If you want a model to deeply internalize medical literature, legal documents, or technical specifications, you feed it raw text in this format, and it absorbs the vocabulary, structure, and reasoning patterns of that domain. The completion format also supports a two-field variant, prompt and completion. This is the classic GPT-2 and GPT-3 style. The prompt provides a starting context, here a Python function signature, and completion contains what should follow. This is the natural format for code completion tasks, where the model needs to learn to continue a code pattern rather than respond to an instruction about it. One important note: the completion format is primarily for base models, models that haven't been instruction tuned yet. If you're working with a modern instruct variant like Llama-3.1-8b-instruct or Mistral 7b instruct, this format is the wrong choice. Those models already expect structured inputs. The completion format is for continued pre-training, domain adaptation, and creative generation tasks on base models. It's less common in everyday fine-tuning projects, but when you need it, nothing else will do. The fourth format is the Q&A format. Straightforward, targeted, and ideal for knowledge-dense applications like FAQ systems and tutoring tools. The Q&A format strips everything down to two keys: question and answer. The question is the query the model needs to handle, and the answer is the complete, accurate response it should learn to produce. What makes this format valuable isn't its simplicity, it's its directness. When you're building a system where users ask specific questions and expect specific answers, training with this format teaches the model exactly that retrieval and response pattern. The Q&A format also has an extended version that adds a context field. This is the foundation of retrieval augmented generation, where the model needs to answer a question based on a specific document or passage rather than its general knowledge. Here's what that looks like. With the context field added, the structure becomes: here is a passage of text, here is a question about it, here is the correct answer. This teaches the model to ground its responses in provided information rather than relying on what it learned during pre-training. That distinction matters enormously for factual accuracy. A model trained with context-grounded Q&A pairs is far less likely to hallucinate answers when deployed in a RAG pipeline. File formats for training data. JSON, JavaScript Object Notation, is the most familiar format for most developers. Your entire dataset lives in a single file, typically as a top-level array under a data key. Each element in that array is one training example. The structure is human-readable, easy to inspect in any text editor, and universally supported by every library you'll encounter. The catch is that to use it, the entire file must be loaded into memory at once, which is fine for small datasets but becomes a real constraint as your data grows. JSON is the right choice when your dataset is small, under 1,000 examples. It's easy to create, easy to inspect, and easy to share. Beyond that scale, the memory overhead and lack of streaming support make it the wrong tool. At that point, you want JSON-L. JSON lines, JSON-L solves JSON's core limitation. Instead of one giant object wrapping everything, each line of the file is a complete independent JSON object. The file extension is either .jsonl or .json. The format looks exactly like your regular JSON examples, just one per line with no commas or brackets connecting them. This means you can read the file line by line without ever loading the whole thing into memory, and that makes streaming possible. You can process a dataset with 1,000,000 examples on a machine with modest RAM because you only ever hold one line at a time. JSON-L is the default format for the vast majority of fine-tuning projects. It's memory efficient, easy to append to, supports streaming, and is trivially simple to create and edit. The trade-off is that large JSON-L files aren't pleasant to read in a text editor, but you're not meant to read them that way. For anything between 100 and 100,000 examples, JSON-L is almost always the right answer. Here's how to create a JSON-L file in Python. The pattern here is worth internalizing because you'll write it dozens of times. Import the JSON module, define your examples as a list of dictionaries, open a file in write mode with UTF-8 encoding, then loop through each example and write it using json.dumps.sa followed by a new line character. That's it. Each call to json.dumps.sa serializes one dictionary to a JSON string, and the new line ensures each example lands on its own line. After running this, open dataset.jsonl in a text editor and verify that each line is a valid independent JSON object. That's your confirmation that the format is correct. CSV, separated values, is the format most people already know from spreadsheets. Each row is one training example, each column is one field. It opens in Excel, it's trivial to create manually, and it works fine for simple datasets. The problem appears the moment your output field contains a comma, a new line, or a quotation mark, all of which are common in natural language. Escaping those characters correctly is error-prone, and multi-line outputs break the row structure entirely. CSV is useful for quick prototyping with simple single-line data. For anything more complex, switch to JSON-L. Parquet is a binary columnar format, not human-readable but extraordinarily efficient. It compresses aggressively, loads extremely fast, preserves data types exactly, and is the standard format in production data science pipelines. The Hugging Face datasets library works with Parquet natively. You need a library to read or write it, Pandas or PyArrow, but that's a trivial dependency. For datasets above 10,000 examples or for any production deployment, Parquet is the right choice. Here's how to create a Parquet file from your training data. This code uses Pandas and the Hugging Face datasets library together. You define your examples as a list of dictionaries, then construct a dataset object by passing the field lists explicitly. The final call, dataset.to_parquet, dataset.parquet, writes the binary file to disk. No output appears in the terminal on success, but you can verify the file exists and check its size. A well-compressed Parquet file is typically 60 to 75% smaller than the equivalent JSON-L, which matters when you're pushing large datasets through a training pipeline. Base models versus instruct models. Different data needs. Base models like meta-llama/llama-3.1-8b or Mistral/Mistral7bv01 are trained on raw text. They're next token predictors. Their training data reflects that a single text key containing raw content, no structure, no roles, no instruction wrapper. When you fine-tune a base model, you're doing continued pre-training, teaching it new vocabulary, domain knowledge, or writing style by showing it more text in the completion format. This raw text approach is relatively rare in practical fine-tuning projects because most people are starting from an instruct model that already knows how to follow directions. But if you're doing domain adaptation, training a model to deeply understand medical literature, legal contracts, or specialized technical content, a base model with completion format data is exactly the right approach. Instruct models like meta-llama/llama-3.1-8 b-instruct or Mistral I/Mistral 7 b-instruct b0 2 have already been trained to follow instructions and hold conversations. They expect structured input. The model has learned to interpret user as the person making a request and an as the role it should play. When you fine-tune an instruct model, you're refining that existing capability, teaching it a specific domain, persona, or task within the structured framework it already understands. This is the format you'll use for 95% of fine-tuning projects. Instruct models, structured data, supervised fine-tuning. The combination of a capable base, a clear conversational format, and high-quality examples is the recipe for a well-behaved specialized model. Choosing the right format for your project. The decision tree for choosing a format is straightforward once you know the rules. Start with your model type. If you're working with a chat model, use the conversational format and save as JSON-L or Parquet. If you're working with a base model, ask whether you have clear instruction output pairs. If yes, use the instruction format in JSON-L. If you're working with raw domain text, use the completion format, also in JSON-L. Then consider dataset size. Under 1,000 examples, JSON-L or CSV is fine. 1,000 to 10,000, stick with JSON-L. Above 10,000, use Parquet. Those three decisions, model type, data structure, dataset size, determine your format every time. Here's how that maps to real use cases. A customer service chatbot uses the conversational format in JSON-L with messages containing system, user, and assistant roles. A code explanation tool uses the instruction format, instruction, input, output, also in JSON-L. A medical Quanda system can use either Quanda format or instruction format depending on whether you need the context field. Creative writing uses the completion format with prompt and completion keys. Domain adaptation for specialized fields uses the completion format with raw text, typically in Parquet for scale. Practical examples. Here's a complete Python example for building a summarization dataset. The training data is a list of dictionaries, each with instruction, input, and output fields. The instruction is always the same task, summarize the text. The input varies per example, different articles, documents, or passages. The output is the target summary. The file is opened in write mode with UTF-8 encoding. Each example is serialized with json.dumps SSA and written with a trailing new line, and a final print statement confirms how many examples were saved. That confirmation line is your first quality check. Make sure the count matches what you expect before moving on to training. This example builds a conversational dataset for a Python tutoring assistant. Each entry in the conversations list is a complete multi-turn exchange, a system message establishing the tutor persona, followed by alternating user questions and assistant answers. The file is written in JSON-L format with ensure_ASCII =false. That flag matters if your content includes any non-ASCII characters like mathematical symbols or code with Unicode identifiers. The final print statement confirms the count. Notice that the structure here is a list of message arrays, not a flat list of instruction output pairs. That distinction is what makes it conversational rather than instruction format. The script handles a common real-world scenario. You have a CSV file of questions and answers, and you need to convert it to JSON-L for fine-tuning. The script opens the CSV with a dict reader, which automatically uses the header row as field names, then iterates through each row, maps question to instruction and answer to output, and writes each transformed example to a JSON-L file. This kind of format conversion is something you'll do constantly in practice because raw data rarely arrives in exactly the shape your training pipeline expects. Common mistakes and how to avoid them. The first and most common mistake is inconsistent key naming. You might start with instruction and output, then accidentally use prompt and response in some examples and question and answer in others. The training library doesn't know these are semantically equivalent. It looks for specific field names. Mixed key names means some examples get skipped or misread, and your training data silently becomes smaller and noisier than you intended. Pick one naming convention at the start of a project and enforce it everywhere. The correct approach is rigid consistency. Every example in your dataset uses exactly the same keys, instruction, and output every time. When you load your dataset and inspect it, every row should have exactly the same fields. Any deviation is a bug. A quick way to catch this before training: load your JSON-L file and check that every parsed object has the same set of keys. One line of Python can catch what would otherwise cost you hours of debugging. The second common mistake is missing context. Here's a conversational example that looks complete on the surface. A user asks about a return policy. The assistant answers, but there's no system message. The model has no idea what store this is, what tone to adopt, or what constraints apply. During training, it learns a generic exchange with no grounding. In deployment, it will give generic answers with no brand voice or domain awareness. The fix is always to include a system message. Here's the same exchange done correctly. The system message establishes that the assistant is a customer service agent for TechStore, sets the expectation for professional and helpful responses, and grounds every subsequent turn in that context. Now, when the user asks about the return policy, the model's response is anchored to a specific identity and purpose. System messages are free. They cost almost nothing in tokens relative to what they contribute to training quality. Always include them in conversational format data. The third mistake is a format model mismatch. Using chat format data to fine-tune a base model, or feeding raw text to an instruct model. A base model doesn't understand row labels like user and an. Those are just arbitrary strings to it, and the role structure adds noise rather than signal. Conversely, an instruct model that already knows how to follow instructions doesn't benefit from raw text pre-training. You're training against its existing capabilities rather than refining them. Always align your data format to the model type. Base models get completion format. Instruct models get instruction or chat format. The fourth mistake is specific to CSV line breaks inside field values. CSV uses new lines as row delimiters, so if your output field contains a poem, a multi-paragraph explanation, or any text with line breaks, the CSV parser will interpret each line break as the end of a row. Your single training example gets split into multiple malformed rows, and the parser either errors out or silently produces garbage data. The solution is simple. Don't use CSV for any data that contains multi-line text. Switch to JSON-L, which handles new lines inside string values without any escaping required. JSON-L handles multi-line content cleanly because the entire example, including any embedded new lines, is serialized into a single JSON string on one line. The new line characters inside the poem become else escape sequences within the string, and the actual line break that separates JSON-L records is unambiguous. When you load the file, json.loads reconstructs the original text with its new lines intact. This is exactly why JSONL is the default format for fine-tuning. It handles the messy reality of natural language data without requiring you to sanitize your content. Hands-on exercise. Time to build something real. Your task is to create a small data set, 5 examples for a recipe modification assistant. The assistant takes a recipe and modifies it according to a specific constraint. Use the instruction format with all 3 fields: instruction, input, and output. Save it as JSONL. Here's what one example looks like. The instruction describes the transformation. Make this recipe vegetarian. The input contains the original recipe with its specific ingredients. The output shows the complete modified recipe with the chicken swapped for chickpeas and the chicken broth replaced with vegetable broth. Notice that the output isn't just a description of what to change, it's the complete, ready-to-use result. That completeness is what makes training examples valuable. The model learns to produce finished, usable outputs, not partial answers. Your 5 examples should cover different modification types. Make it vegetarian, make it gluten-free, make it healthier, double the quantities, and add a spicy variation. Each one needs a distinct recipe as input and a complete modified recipe as output. The variety matters. It teaches the model to handle different types of modification requests, not just memorize one pattern. Here's the complete solution. The dataset is a list of 5 dictionaries, each with instruction, input, and output keys. After defining the data, the code saves it to recipe_dataset.jsonl using the standard JSONL write pattern json.dumps_srv with ensure_ASCII equals. Then it reads the file back and prints each example's instruction, input, and output. That readback step is the verification. If your data round trips correctly through write and read, it's properly formatted and ready for a training pipeline. Here are the answers to the format selection exercise. A code completion base model uses the completion format, prompt and completion pairs, or just raw text. A customer service chatbot with multi-turn conversations uses the conversation format with system, user, and assistant roles. Teaching a model to output structured JSON uses the instruction format, where the output field contains valid JSON strings. A FAQ answering system works with either Q&A format or instruction format depending on your preference. Medical domain adaptation uses the completion format with raw text. You're doing continued pre-training to absorb domain vocabulary and reasoning patterns, not teaching the model to follow instructions. Quick reference. Format comparison. Here's the complete picture in one place. The instruction format uses instruction, output, and optionally input, best for task completion with instruct models. The conversational format uses a messages array with role and content objects, the standard for chat models and multi-turn interactions. The completion format uses either a single text key or prompt and completion keys, the right choice for base models and text continuation tasks. The Q&A format uses question and answer, clean and direct for knowledge retrieval and FAQ systems. Know these 4 cold and you'll never be confused about how to structure your training data. Key takeaways. 5 things to carry forward from this lesson. First, match your format to your model type. Base models need raw text and completion format. Instruct and chat models need structured formats. Second, use JSONL for most projects. It's memory efficient, streamable, and handles complex text without escaping issues. Third, be rigidly consistent with key names throughout. Fourth, always include system prompts in conversational format data. They're what give your model its identity and constraints. Fifth, choose your format based on the task. Instruction for task completion, conversational for multi-turn chat, Quanda for knowledge retrieval. Knowledge check. Before moving to the next lesson, make sure you can answer these 5 questions without looking anything up. What are the 4 main data formats for fine-tuning? When do you choose JSON-L over JSON? And when does Parquet make more sense? What's the structural difference between the instruction format and the conversational format? Why do system prompts matter in chat format data? And what format should you use for a base model versus an instruct model? If any of those feel uncertain, rewatch the relevant section. This is the foundation everything else builds on. Assignment. Assignment. is assignment. Through careful analysis and practice, you'll master these techniques quickly. Your assignment is to create a mini dataset of 10 examples for the fine-tuning project you actually want to build. Think concretely about what you're making. A customer service bot, a code helper, a writing assistant, a domain expert in law or medicine, or your specific technical field. Choose the appropriate format for your use case. Save it as JSON-L, verify that it loads correctly, and write a one-line comment on each example describing what specific behavior it's teaching the model. That documentation habit will pay dividends when your debugging training runs later. Here's starter code to build from. The starter code gives you the complete JSON-L write pattern with one addition, a verification step at the end. After writing the file, it reopens it, counts the lines, and prints a confirmation with the total. That line count is your first sanity check. It should match the number of examples in your list exactly. If it doesn't, something went wrong in the write loop and you want to catch that now before you hand this data to a training pipeline. Make it a habit. Always verify your dataset file immediately after creating it. What's next? You now know how to structure training data in any format a fine-tuning pipeline might require. The next step is learning how to work with that data at scale, loading it, filtering it, transforming it, and feeding it efficiently into a trainer. That's what Hugging Face Datasets gives you, and it's the industry standard tool for exactly this job. Continue to Lesson 3.2, Hugging Face Datasets. Additional resources. If you want to go deeper, the Hugging Face Dataset Formats documentation covers every supported structure in detail. The JSON-L specification is a quick read and worth knowing precisely. The chat template guide explains how different models tokenize conversational data, important when you get to the training stage. The Alpaca dataset is the canonical example of instruction format done well, and ShareGPT is the reference implementation for conversation format. Both are worth reading through to calibrate what high-quality training data actually looks like. Here's a format comparison worth keeping in mind as you make file format decisions. JSON-L leads for most fine-tuning work. It's human-readable, supports streaming, and handles nested structures like the conversational format's messages array. Standard JSON shares the readability but loses streaming. The entire file loads into memory at once. CSV is compact and spreadsheet-friendly, but breaks on nested structures and multi-line text. Parquet trades readability for performance. Binary, compressed, with fast random access and exact type preservation. The Hugging Face dataset format combines Parquet's efficiency with native integration into the datasets library, making it the most capable option when you're working at scale with Unsloth. Match the format to your dataset size and your toolchain, and you'll never be fighting your file format during training. This screenshot shows a real-world instruction format example from a medical domain dataset. The instruction key specifies the task, summarize patient discharge notes. The input key contains the actual clinical text, specific details about a patient's condition, treatment, and discharge status. The output key contains the target summary the model should learn to produce, concise, accurate, and clinically relevant. Notice how the output is not a paraphrase of the instruction. It's a complete standalone piece of text that directly addresses the input. That completeness is what makes the training signal clean. The model learns to produce finished, usable outputs, not partial responses. This diagram shows the full data preparation pipeline from raw sources to a running trainer. Raw data arrives from multiple directions: PDFs, web scraping, SQL or CSV exports, manual annotations. All of it flows through a cleaning and normalization step first. That central hub is non-negotiable. Inconsistent formatting, encoding errors, and duplicate entries all get resolved here before the data takes any final shape. From there, the data is structured into JSON-L instruction pairs and loaded using datasets.load_dataset_them. The dataset.map SAA function handles any. The final destination is SFD trainer from the unsloth library, which is exactly what you'll use in the upcoming training lessons. Understanding this pipeline end to end means you'll never be confused about where your data comes from or where it needs to go. Here's a storage comparison for 10,000 training examples across different file formats. Pretty printed JSON comes in at 120 MB. The overhead of white space and indentation adds up fast. Compact JSON-L drops to 85 MB by removing that formatting. CSV comes in at 70 MB for simple flat data. Uncompressed Parquet lands at 60 MB, and snappy compressed Parquet drops dramatically to 22 MB. The Hugging Face dataset format, which uses memory-mapped arrow files, comes in at just 18 MB. The pattern is clear. As your dataset grows, format choice has a direct impact on disk usage, network transfer time, and how quickly your training pipeline can load data. For small datasets, the differences are negligible. For production scale work, they're significant. This diagram shows the anatomy of a well-formed JSON-L file. Each line is a complete JSON object. No commas connecting lines, no wrapping array. The three fields, instruction, input, and output, appear consistently on every line. The examples cover different task types: translation, summarization, creative writing. That variety is intentional. A diverse dataset teaches the model to generalize across task types rather than overfit to one pattern. The JSON-L format makes this easy to build incrementally. You can append new examples to the file one line at a time without rewriting the entire dataset, which is a significant practical advantage when you're collecting data over time. The Alpaca format is one of the most widely adopted instruction format conventions, and understanding its fields precisely will help you work with a large portion of publicly available fine-tuning datasets. The instruction field is required. It's the task or question. The input field is optional. It provides additional context or content for the model to work with. The output field is required. It's the target response. There's also a text field that combines all three into a single formatted training prompt, typically following the template. Below is an instruction, input, response. Many datasets on Hugging Face use exactly this structure, so recognizing it means you can load and use them immediately without any field remapping. The ShareGPT format is the conversational counterpart to Alpaca. It's the standard for multi-turn dialog datasets. Instead of flat instruction output pairs, ShareGPT uses a conversations array where each turn has a role and a value. The roles are system, human, and GPT. Note that ShareGPT uses GPT where the Hugging Face chat template uses AN. In this Python tutoring example, the system message establishes the tutor persona, then the human and GPT turns alternate naturally. The human asks how to read a file. The model explains the open function. The human follows up about error handling, and the model explains try/except. This back and forth is exactly what the conversational format is designed to capture, and ShareGPT datasets give you thousands of examples of it done well. Different frameworks use different field names for the same concepts, and knowing the mapping prevents a lot of confusion when you're working across datasets and libraries. What Alpaca calls instruction, ShareGPT stores as conversation zero value. What Alpaca calls input, other datasets might call context, document, or passage. What Alpaca calls output, ShareGPT stores as conversations minus one value. The underlying concepts are identical: task, context. When you load a new dataset and the field names don't match what your training script expects, a quick dataset.map ASAE call to rename the columns is all you need. Understanding these mappings means you can work with any publicly available dataset without being blocked by naming conventions. This decision tree gives you a repeatable process for format selection. Start with one question: does your project involve multi-turn conversations? If yes, share GPT conversational format. If no, ask whether your data has extra context or input beyond the task itself. If yes, Alpaca format with all three fields. If your data is purely task and response with no additional input, Alpaca format with the input field left empty. If your data is raw text with no task structure at all, completion format. 4 questions, 4 outcomes. Run your training data through this tree before you write a single example, and you'll never have to backtrack and reformat your entire dataset because you chose the wrong structure at the start. This diagram shows the data validation pipeline you should run on every dataset before training. The flow starts with loading your JSON or JSON-L file, then immediately runs schema validation, confirming that every example has the required fields and that no required field is null or empty. From there, a lens check filters out examples that are too short to be informative or too long to fit within your model's context window. Deduplication removes exact or near exact copies that would cause the model to overfit to specific phrasings. Sample inspection is a manual step. Read a random selection of examples with your own eyes and confirm they look correct. At any stage, examples that fail a check get flagged, logged, and either fixed or filtered out. Running this pipeline before training is the difference between a clean training run and a confusing one where you can't tell whether poor results come from the model, the training config, or the data itself.